Welcome guys, I am here with you to solve this problem number 37 of CSIR NET June 2019. So let us firstly read this question. This is actually a question from the number theory. So let us solve it. For any integer n greater than equal to 1, let dn represents number of positive divisors, vn represent number of distinct positive divisors, and wn represent number of distinct positive divisors, number of prime divisors of n counted with their multiplicity. So these are your three notations that the question is using. Now these are your options what you have to choose. So firstly, by giving few examples, I will make these terms familiar to you. Okay, so let us see what are these terms. So if I take my n to be, let us say, a prime square. Okay, if I choose n to be a prime square, then what will be dn? Dn actually represents number of prime divisors of n. That means how many prime divisor it has. So not prime divisors, it actually represents number of positive divisors. So you know that if your n is prime square, then it can only have 3 divisors. Okay, 1 p and p square. Therefore dn is actually 3. Now see, if your n is prime square, then what will be your Vn? Now Vn represent number of distinct prime divisors. Now you know that for this n, you have only one prime divisor, that is p itself. Therefore, this value is actually equal to 1. Now what will be Wn if n is p square? Wn represents number of prime divisors of n counted with their multiplicity. So you see n is actually equal to p dot p. So p is a divisor, but it has multiplicity 2 in this case. Therefore Wn will be 2. You can take another example, p cube. If you take p cube, what will be the value of w? So w will be 3 in this case. In this case, v of n will be, okay, v of n will be, how many prime divisor it has? If you take n is equal to p cube, it is still 1. You are getting my point. For this n, your Vn is still 1. But Dn for this case will vary. Dn will be how many divisor it has? 1, p square, p cube. So you got 4 divisor. Therefore, you get 4 value here for this number, right? So now I think you are familiar with these terms. Now we can proceed with the question. So I will erase firstly these examples from here. Okay, now let us quickly see your first option. What your first option actually suggests you? It suggests that if n is greater than 1000 and Wn is greater than equal to 2, then Dn is greater than log n. It says that Dn, your first option, it says Dn is actually greater than log n. Do you think it's correct? I don't think so, because Dn for a prime, okay, let us take a case. If you choose your n to be a prime number satisfying, let us say, these two conditions, then your Dn, okay, then their Dn will be 3, not 3, it will be 2. So I am saying that if your p, if you are choosing your p to be greater than equal to 1000 and you choose n to be, let us say, p, then your Dn will be just, okay, it will be just 2, because how many positive divisor it has? It has only 2 positive divisors. But if you figure out the value of log for this p, since p is greater than 1000, if you figure out the value of log for this p, now what do you know about log? Log is actually an increasing function. You know that? So for just e cube, its value is 3. Log e4 is, you know these values, right? Log e4 is 4. I am taking the natural log here. Okay, log e4 is 4. So for this n, okay, for this n, your Dn is just 2, but log p, since log p is greater than 1000, therefore log p will always be greater than 2. Okay, you are getting my point? So this is the thing that you will get intuition to how to make counter example for this question. Okay, but in your question you need Wn to be greater than 2. So you cannot directly choose p, because for p your Wn is 1. Okay, so I will take n is equal to p square as your counter. Okay, now if you will have p square, then your Dn is greater than equal to, not greater than, your Dn will be 3. Okay, now let us figure out the value of log. log of p square. So log of p square will be 2 times of log of p. Now since p is greater than 1000, right, since p is greater than equal to 1000, therefore it must be greater than 3. So this is what I am contradicting. So dn is just 3, but it is not greater than log of p square. Okay, just erase n, just write p square here. Okay, so therefore this statement is actually a false one. You are getting my point. So first one is false. Now let us come back to the option number. Firstly, I will go to the option number 4th and then I will proceed. Let us go to option number 4th. So what option 4th suggests you that Wn is equal to Wm, then dn is equal to dm. It says that if your Wn is equal to Wm, then dn is equal to dm. So I will take just this example. Just take your n to be 2 square and m to be 6. Then for these two numbers, your Wn will be 2. Okay. But if you figure out that your dn for n is equal to 2 to the square, it will be 3, but dm will be, okay, dm will be 4. Okay, how many divisors 6 has? 1, 2, 3 and 6 itself. Okay, so therefore this option is false by taking this as your counter example. So let us remove 4th one from here. Okay, so now come back for the option number 2 and 3. Now see, doing these two questions by example are actually easy, because you can just take out an example and then see whether it is happening or not. But for this one, for the option number 2, you see they are saying there exists a natural number n such that dn is greater than 3 root n. So you cannot check, okay, you cannot check every natural number. You are getting my point? You have to see whether dn is greater than 3 root n for a number. It is not saying that it is happening always. It says there exists a natural number. So you cannot contradict this by taking counter example, because they are saying that there exists a number. So you have to prove something like this. Okay. So what I am claiming, for all n belongs to natural number, okay, the proof for this question, this option will be little bit long, but I will do it quickly. For all n belonging to natural number n, your dn is actually less than equal to 2 root n plus 1. Okay, this is what I am claiming. So by this claim, your question is done. Okay, so it says there exists a natural number such that it is greater than 3 root n, but I am claiming that for every natural number it is less than 2 root n. Okay, I will prove this, but from by this claim your second option is false. That means your third option is correct. Okay, now let us prove this one, this claim firstly. So I will make two cases. Okay, your natural number can be perfect square or it cannot be a perfect square. So I will take the first one, that if n is equal to m square for some m belonging to natural number, that means it's a perfect square. So now let us figure out how many divisor it will have. Okay, now see, I will draw a number line for you. This is your n. Let us say this is your 0. So m will lie somewhere here. Okay, now what I am claiming, okay, what I am claiming, that number of divisors that are present before m are actually equal to number of divisor that are present here. Okay, I am proving this claim, and I am repeating myself. I am proving this claim right now. So I have taken case number 1 where n is perfect square, and then I will take another case where m is not a perfect square. And for this case, you know that m is a natural number, so m is a divisor. Okay, you know that. So m has to lie somewhere here. So now what I am claiming, that if a divisor is present here, then it is also present here. For this divisor there exists a divisor here also. So I will write it firstly. I will say this is an exercise for you. Okay, these are the some little exercise I will always give to you. That's why you can be your thinking will be strong if you will solve these type of exercises. What I am saying, that if A is a divisor of n, then n by A is also a divisor of m. Okay, this is an exercise for you. Not m, sorry, it is n. I am saying that if A divides n, that means if A is a divisor of n, then n over A is also a divisor of m. This is your first exercise that you need to prove yourself. Okay, otherwise this video will be too long. Now let us see exercise number 2 that I am giving you. Exercise 2 says A divides n and A is less than m. This will imply n by A divides n and n by A is greater than m. Okay, so these are the two things. Okay, these are the two easy things that you will prove yourself. Okay, these are the two easy things that you will prove yourself. So by using these two exercises, what you can directly say, that if a divisor is present here, then with respect to that divisor there exists a divisor here. Okay, so if A is a divisor here, then n over A will lie somewhere here. You are getting my point? So for every divisor here there is a divisor here of n. So you can directly say from this thing that number of divisor of n less than m, okay, is equal to number of divisor of n greater than m. This is what I am saying. Okay, for every divisor A there is a divisor n by over here. Therefore total number of divisor which are less than m is actually equal to total number of divisor which are greater than m. You are getting my point? Now let us come back to the question. Okay, so these are the things you have to prove. So using these two exercises you can write this one. Okay, now see how many divisor it will have. So total divisor of n is actually equal to number of divisor less than m plus number of divisor greater than m. Now you know for a perfect square case m is also a divisor, therefore you have to add one more to it. Okay, so total number of divisor of n will be equal to number of divisor, because what do you know that if you have taken divisors less than m, all the divisor less than m and greater than m, and that m itself is a divisor, then you have chosen all the divisor. Okay, then that's why I can write this thing. Now you know that these two quantities are equal. That means what is total number of divisor? It is actually dn. So dn is actually equal to 2 times of number of divisor less than m plus 1. Okay, now you know that a divisor which is less than m must lie somewhere here. Okay, it must lie somewhere here. So let us say these are your divisors. Okay, a1, a2, a3. Okay, these are your divisor. Now if you will count these divisors, that counting will always be less than m. You are getting my point or not? If you will count these things, that quantity will always be less than m. So you can replace this thing and place an inequality here, that number of divisors can be replaced by m, and you have to put here less than here. So from here you can directly say this thing. Okay, because number of divisor you are taking for less than m, that means you are choosing specific numbers from here, and though if you will count them, that how many are there, so if you will count them, that counting will always be less than m. Therefore you can say that dn is less than equal to 2m plus 1. That means this is actually equal to 2 root n plus 1. So for this case you have actually proved that dn is less than equal to 2 root n plus 1. Now let us see the case where n is not a perfect square. So if it is not a perfect square, then what will be the changes that you will made in the question? Okay, that you will made in this proof. So if it is not a perfect square, the only thing you have to change is you have to replace m with root n. Okay, this is the only thing that you have to replace in this proof. So if if you are replacing root n with m, that means in the case number 2 you have to replace this one also, because root n is not an integer if it is not a perfect square, therefore this one will not be there, otherwise the whole proof will go through. Okay, so for case 2 your dn will be less than 2 root n. Okay, so using these two cases you can directly prove this thing. Okay, this is okay, use this case and this case, then it's done, your claim is done. Okay, it's done. So by this thing you have proved. Okay, so I was proving that your second option is actually false, because it says that there exists a natural number such that dn is greater than 3 root n, but I have proved that dn is actually all, for every natural number your dn is less than 2 root n plus 1. Okay, this is what I have proved. So now I will erase this thing and I will directly come back for the option number 4. Okay, see this proof yourself, okay, and try to figure out it yourself, then you will get a very deep intuition about this question. Okay, these are the calculation you can always do in your mind yourself. You are thinking that this question is little bit long, but it's not, because if you'll do it yourself next time, this question you will do it just 1 or 2 minutes. Okay, now let us see why your third option is correct. It says that for every natural number you have 2 to the power of Vn is actually greater than Dn is actually less than 2 to the power Wn. Okay, now what are the things that are required for this option to prove? Okay, I am proving this one. So the only thing that is required is this note. You know that fundamental theorem of arithmetic, what it says, that if you have a natural number, then you can always write them as a product of distinct prime. So this is what I have used here. Let n belongs to natural number, then n is equal to p1 to the power alpha 1, p2 to the power alpha 2 up to pk to the power alpha k. Now from this, what my note is claiming, that total number of positive divisor is alpha 1 plus 1, alpha 2 plus 1, alpha k plus 1. Okay, this is the thing that you have to remember, otherwise you can figure out it yourself using combinatorics. Okay, so what this note actually says, that if you have a natural number, then it can be always be written as product of primes. Now using this one you can directly write that total number of positive divisors are like this. Okay, so I will keep this note here. Now you have to prove this, that for every natural number this thing happens. So now since n is a natural number, therefore what you can do, you can write it in product of primes. Okay, distinct primes, p2 alpha 2 up to pk alpha k, where alpha i's are greater than equal to 1. Now let us see what will be dn for this case. So dn will be, using that node, dn will be alpha 1 plus 1, alpha 2 plus 1 up to alpha k plus 1. Okay, so these are the values of your dn. Now let us see what will be your vn for this case. So vn represent number of distinct prime divisors. So number of distinct prime divisor will be k. And what is the value of wn? Wn will be number of prime divisor of n counted with their multiplicity. Now you know that p1 is a divisor, but it has multiplicity alpha 1. So wn will be alpha 1 plus alpha 2 up to alpha k. Okay, you are getting my point. So now let us figure out. I will remove it. So now let us see what is your 2 to the power n, vn, sorry, 2 to the power vn. So vn is k, so it can be written as 2 to the power k. You can write 2 to the power k as 2.2.2 up to how many times? You can write it as k number of times. So from here you are getting this thing. Now see, this 2 can actually be replaced with alpha 1 plus 1. Alpha 1 is greater than equal to 1. That means this number is always greater than 2. So this number can be replaced with this thing. The only thing that is required is this inequality. Okay, so this thing is equal to this, and 2 is less than this one, next 2 is less than this one, alpha 2 plus 1, and this one is less than alpha k plus 1. You are getting my point or not? 2 to the power Vn is like this, and every number is less than this, so their product is also less than this. And what is this number? This number is actually Dn. So the first part of your proof is done from here. You are getting my point? Now let us prove part number 2. Now see, your Dn is actually equal to, okay, I will partition it. Your Dn is actually equal to alpha 1 plus 1, alpha 2 plus 1, and this is alpha k plus 1. Okay, now I am using a result, and what is that result? You always know that 2 to the power x is actually equal to x plus 1, is actually greater than equal to x plus 1. This is the result that I am using in this question. Now see, from here what you will have that now alpha 1 plus 1 will be smaller than 2 to the power alpha 1. This thing will be smaller than 2 to the power alpha 2 using this note, and this thing will be less than 2 to the power alpha k. So from here you will get it is less than 2 to the power alpha 1 plus alpha 2 up to alpha k. And what is this number? This number is nothing else, this is 2 to the power wn. So here you have proved your part 2. So from these two things, this one is correct. Okay, so to prove second and third option, it is little bit tricky, but still you can do it with your intuition. Okay, I have not done anything very different or out of mind. Okay, these are the things, basic thing you have to do in your exam. But this question, for exam purpose, this question will take you about 5 to 6 minutes. So if you can do other question, I will suggest you to do other question then because seeing these and these option is not easy. Okay, it's not very trivial that you can directly tick that second is false and third is correct. Okay, seeing this option and this option is very easy. Okay, it can be directly discarded, but proving these two things are little bit tricky. So I will suggest you in the exam that if you have time and you don't know any other thing, these are the question in which you can spend time, because you don't need any theory here. All I have done is just intuition. Okay, therefore you can do this question. Okay, so thank you guys.